So, hi everybody, I'm Tom Anschutz. I'm with AT&T, and it's my pleasure today to have two topics, not just one. And so I have first a run through of some of the AT&T specs, and I promise you there's going to be something new and exciting here since the last time you saw these charts at the summit a few months ago. And we have a second talk as well. As you know, on the previous calls here for the Telco working group, there was a topic that came up around universal CPE. And like a fool, I opened my mouth and said, well, you know, AT&T is really interested in universal CPE. We do some of that stuff. And so I actually got sort of our spirit and intellect from John Gibbons, who will come up and talk a little bit about universal CPE as a sort of second topic. Okay, and I'm really hopeful that this can be interactive, so please feel free to raise a hand or say something or interrupt if you will. All right, so I'm going to go through the charts that you've seen before or had a chance to see before a little more quickly so that I can get to sort of new material as well. And as you know, we have a number of specs that we're kind of progressing or have brought along within the Telco working group. And there are sort of, you know, what possessed us to do that kind of questions that people usually come up with. And these are sort of the top level answers. In a lot of cases, what we found is that we're kind of trying to create something new. It hasn't necessarily been in the marketplace. We're not creating a white box version of something that already exists. We're trying to disaggregate network elements and create things that haven't existed before in a real way. And so what you'll find as sort of themes through all of the specs that we have are the following items, that we kind of minimize the software and the state in the box so that it can stay in servers where we can use different software techniques for availability and simplification, and that we separate access from aggregation. So you don't bundle multiple types of functions that are in a box or previously were in a box in the new sort of disaggregated model. And what that allows you to do is really kind of recompose how you would put together large systems, things like the M cord or the R cord, you know, end-to-end subscriber broadband access or mobile access. In our hardware design strategies, we look for things like removing memory and flash from the individual boxes. If you think about it, if I have to deploy lots of ports of GPON or XGS-PON, I'm going to put a lot of those boxes into the rack. And if I can defragment the sort of wasted memory and flash in those boxes and kind of pseudo-centralize that, I have an opportunity to become a lot more efficient in those types of designs than I was before. One of the things that we're eager to do is bring BMCs to devices that they haven't seen before. So not only in a server, and not only in a top-of-rack switch, but imagine having a BMC in your GPON blade or a BMC in your G.fast DPU. We think that those are real good reasons for doing things like that. And then finally, and probably sort of full circle here, is to run the control and management in a separate computer, where in the past, the control and management sat right on the box. If we pull that out, we can reduce the memory and the footprint and the storage and the flash in the box, but we can also have the sort of centralized kind of control, the concept behind SDN, right? And directing that many instances of that hardware from a set of common computers. Okay, so why don't we have a look at what the specifications are? And these are in opposite order than you might have seen them in March. First, I'm going to go through a set of G.fast specs. And as you recall, last time I presented, one of the things we're looking for is what Bill always talks about, is partners that want to travel along this path. And one of the things I'm happy to say is that I don't know if I'm at liberty to mention them, but we found someone who's also interested in the single port GPU, and so there's someone that we're working with, another carrier in that space. Incidentally, AT&T, the folks back home that tell me what to do all the time, are really interested in the 16-port GPUs, so we've got sort of two ends of this bracket well covered. What do these things look like? All right, so here's a GFAST 16-port GPU. It's typically used in multi-dwelling units, apartment complexes and so forth, and it allows you to use coax or twisted pair to provide consumer broadband service and small business broadband service. For folks, how many people know what G.fast is? Okay, so for other folks, G.fast is sort of the current best gen or next current gen of DSL. It allows you to get up to multiple gigabits of speed over twisted pair copper if it's short enough. And it also works, interestingly, really well over coax. And so in an MDU, there might be existing wiring that's either coax or copper. If you've got the coax facility, it has some benefits for that. And if you have copper, then it works twisted pair that works really well. In deploying that, you actually have a lot of scenarios. You want to be very flexible to be able to address lots of different kinds of existing dwelling units, and some of them have video over their coax in addition to the broadband. Others don't. And so what we've done is create a design where there's a common logic board, as you see at the top, which would have your uplinks in an SFP cluster and a switcher network processor that aggregates multiple G.fast silicon, and then you have 16 ports of that technology. Now there's a connector. The blue connectors here show that for a common logic card, we'd be able to plug in multiple different kinds of physical variations. So the big one is that you might have twisted pair or coax. And then the secondary items are that you might have reverse power, meaning that the unit is being powered from the customer's ports, not from a local power supply. And the second thing is that you may have a video distribution over the coax in addition to G.fast. And that's what you see in the bottom in terms of RPF is the reverse power feed unit, and the triplexer is an item that would bring satellite signals together with the G.fast signals for home delivery. All right, so spending a lot of time on that, you can imagine that an 8-port unit is not a lot different than a 16-port unit. And as you'll realize that this game gets played over and over again, a 4-port unit is slimmer yet. The interesting thing, though, is that as you get down to 4 and 1-port units, you start wondering whether or not you really need to have an aggregation device, or whether you could use the silicon that's typically used for the uplink, which is usually GPON or XGS-PON, and use that for the network management of the GFAST. And that's exactly what these designs look like. Of course, I wouldn't want to rob you from the picture of the single family. The single port DPU typically is described as fiber extension by a lot of folks, meaning that fiber will come to the home. So it might be a normal fiber to the home environment, but getting the fiber into the home winds up being some kind of problem because it's a historical home or a historical place, or the customer just doesn't want you to be drilling or perforating their house. And so what often happens is you bring the fiber right up to the edge of the home, and then you take either coax or existing twisted pair to get just inside. And at those really short loop lengths, G.fast does a great job of doing that. Okay, any questions or comments about G.fast? Really good at putting me to sleep too. I'm sorry about that. Okay, so here we go. The second part of the talk is going to go a little bit into our PON specifications. So here's where you'll see something new. In the previous slides from March, we had 16-port and a single port device, and now you'll hear about a 24-port pizza box as well. And from the discussions earlier, one of the things about deployment deployments and trials and so forth, AT&T has been working on the spec and has had a number of interactions with different potential suppliers, largely around the 16-port pizza box, and it's gone really well. We've been really pleased with that. A number of folks have also come in with alternate technologies that will allow us to grow to 24-port, and while we had originally had a fairly dim view of that, it's improved significantly, and so now we have a new spec that we'd like to bring forward there for that. So what does that look like? Well, it's not a big surprise that it looks a lot like the 16-port box, but with 24 ports. And once again, to get that kind of density, you use an FPGA instead of the merchant silicon. We've had, I guess we're still kind of squeamish about FPGAs and how do they fit into OCP specs, how do they fit in an open environment, and really it's not just about that silicon, it's also about the software or the configuration of that silicon that sort of dictates in our mind whether this is an open or enclosed environment. And other than that, it looks very similar to the other boxes you've seen before, the redundant hot swap power supplies and fans, a COM Express option for the CPU, and AEMC, like I was mentioning earlier. Okay, what we're still thinking about is whether or not to use an ASIC or an NPU for aggregation, and whether or not with FPGAs we could actually run the driver firmware remotely, like we've been able to do with the various merchant silicon designs. So the functional block architecture for this looks pretty straightforward. The FPGAs provide a PHY, can basically turn an XGS PON interface, or 4 of them, into the appropriate Ethernet analogs or lanes that will go back into either an ASIC or an NPU for application. All right, you also have timing and control in a local BNC or CPU option. And after that, we have still the 16-port box. And this is the one that I mentioned earlier. We've had a fair amount of experience, and we've gone through a number of trials in the lab. So we've seen hardware for this design, and really pleased, and still moving forward with this technology. And it's as you can see, we still have the same open questions. So if you're looking for something to either ask me about or comment on, one of the things that we had in the design is a PCI switch, which would allow you to connect all of the sort of control paths from the different merchant silicon devices inside the box to a single CPU. And what we're wondering is sort of the trade-off between using that PCI Express switch or wiring or using a CPU that has more PCI Express lanes to begin with. And once again, we're fairly bullish that we'd be able to bring the firmware out of the CPU on the box and into adjacent servers over time. But at the moment, the ones that we're testing and working with still use an embedded processor for the driver software. Okay, so what happens if you take you love my outside box. If you take the XGS PON, you bring it down to a 4-port clamshell. It's very similar to the previous spec. However, once again, with a smaller deployment and an outside plant, you wonder, do you actually incorporate a separate physical BNC, or do you make that a software layer and try to create a virtual set of BNC functions in the device? And then finally, the smallest XGS PON device is the Pluggable. This is in the form factor of an SFP Plus, and as you can see, it has some extra heat cooling fins that allow it to sort of hang out over the typical switch, and then allows it to sort of be used in existing devices where you can have the space for those fins. Question?
Yeah.
Or comment?
On the previous slide, you put the bullet there, PCI switch versus CPU choice. Can you talk about that a little?
Okay, so once again, the question was, the merchant silicon used in this design and the one before has PCI Express as a natural way to command the SOC chips that either do the, well, in that spec, they were the Broadcom Maple XGS PON merchant silicon and the Qumran aggregation switch. And all of those are controlled through a PCI Express lane to a centralized CPU. And right now they're aggregated through a PCI Express switch, like you find in the server. And the question is, what's the better trade-off? Would you be better off to have a switch and then have maybe a less powerful processor with fewer lanes? Or would you be better off to remove the switch and bring all the lanes in individually into higher-end CPU that had more of them to begin? Does that make sense?
Yep. What about multi-CPU?
What about multi-CPU? Yeah, that's a great question. Thank you. So we've been thinking about what would, so between the BMC and a CPU on a Common Express module, do you want to have more than one CPU? And so our first most desirable model is where CPUs could be external from the box, that you don't have to have the drivers running inside the box and not have to worry about failing over CPUs. In that model, we can use standard cloud techniques, and I'll talk about it at the end here. We can use Bolsa as a sort of scale-out, highly available software stack that manages from other servers, and where the server can go out and it wouldn't take the driver away. However, if you got to put the software into the box, the question becomes sort of a slippery slope. You run it on a CPU that's sort of a control processor, and then what if that fails? You lose the whole box. Could you fail over remote control through the BMC? And then you think, well, that means I want maybe to connect the BMC with PCI Express lanes too, so that it can manage these devices. And then you start thinking, well, should I put two processors in here instead? So yeah, that's kind of an interesting space to think about if you are of the mind that you need to have the CPU and the driver software running inside the box, not disaggregated. Then I think it becomes a real question whether or not you can use or desire to have multiple CPUs. It would be interesting, if I can pop the question back, it would be interesting to think about whether something like a Common Express module would help with creating sort of a common motherboard that has all of the aggregation and merchant silicon, PHYs. But then, depending on which module you plug in, you might have one low-end CPU or high-end CPU, or even a dual, some kind of failover module with probably some kind of PCI switch on it. Yeah. Okay, thanks for the question. Okay. Any other questions or comments? Oh gosh, now we got it. Hi, Jeff.
What was the reasoning for specifying that PGA for the 24 Was there a technical reason for that?
Yeah, we thought that for that box with a one rack unit size, that the power in the cooling wouldn't let you get to 24 ports with the merchant silicon.
So
With today's silicon. There's always tomorrow. Right? That's a good point. Okay. Yes?
It's remote to not having a CPU in the box.
Mm-hmm.
Are you referring to the independent, basically having everything go in there, or PCI some other?
Okay, so the question for people who didn't hear it was, see if I got it right first, was, okay, I heard you talk about no CPU in the box. What's up with that? And are you going to communicate with the silicon in-band and so forth? And the answer is yes. I do think I'm going to communicate with the silicon in-band. One of the things that has come up, when when we create this control and management software outside of the box, one of the things that we will run into is that you want highly available control plane paths into that silicon. And what that means is that you probably don't want to do open flow through just one management port on the back of that kind of a device. And of course, the way we're pulling the software out, you don't even do open flow. What you're doing is the basic in-band network API calls for the silicon through an in-band path. And so we were more or less forced.
Is that the right picture?
No. On this one, right? No out-of-band port. And not a lot of CPU, there is a CPU on there, believe it or not, but not a lot of ginormous software stack that we can do there. So we were more or less caged into software architecture where we can drive the silicon from remote. And it looks really good from an availability perspective. And the silicon we're using in these other boxes also looks like it's going to be possible to manage in-band from remote. And it is what we've done with the GPON box that came before these as well. The network got really well. Okay, any other questions?
Are there any specific environmental conditions requirements for this platform?
The question was, are there specific environmental requirements for these devices? And the answer is yes. On a previous call, I think it was, we have two different specs that were derived from the original nets that take what can go into our central offices. And the two specs that we shared them with, if you go to our Telco wiki page, you can get to those specs. There are links there to the AT&T sites. But generally speaking, the two specs follow the following pattern. In the first pattern, if it's a device that can that doesn't provide a single point of failure, it's for example a server or a disk, and I can fail over a software function to an alternate server, an alternate disk, then that has a fairly moderately relaxed set of requirements. On the other hand, and these boxes all fall into that, if there's a device that doesn't really fit that model, and neither the XGS PON or the GFAST fit this because they are the single serving point for a given customer, right? Their PON terminates there and can't easily fail over to another box, or their GFAST twisted pair can't easily fail over. These have still more stringent requirements, closer to what classic nets was, but not completely there either. Okay. Is that it? Okay. And the last section here was about open software stack. We heard a little bit about this earlier. You know that we've been engaged with ONOS and with Korg and with Bolsa. And I will show you then is here that we've got an access software architecture we've developed around this, where we develop high-level features and functions. And when I say a high-level feature or function, I'm talking about things that you used to think about access nodes providing, like authentication or multicast control. And we want to do these at a very high level and independent of underlying access media types. And we believe that's going to give us operational advantages over time, in that they won't be unique variations of the theme based on what PHY that we decided to deploy that year. So there is this thing called Bolsa, which was a VoLT hardware abstraction, and that acts as an isolator between sort of the specific capabilities that would come from merchant silicon, and kind of an agnostic, hardware abstracted layer that we would expect across all kinds of different silicon. So the Bolsa then has these drivers that plug in to manage silicon from multiple providers, but at the other direction, northbound, it creates interfaces like NetConf and OpenFlow or even others. And these interfaces remain the same across all of these devices. So that's our managing the amount of complexity and diversity that get offered into our orchestration and management systems, even though we have potentially multiple different kinds of software from multiple providers at the very low level. Okay, and I think the other thing you should notice here is in February, I don't know if we mentioned this in the OCP summit, we were able to convince the folks at Owen Lab and to add G.fast technology to this software stack. So it's no longer just a PON stack, it's PON and G.fast. They're usually used in conjunction anyway, with PON being sort of the backhaul or the uplink for G.fast units. So there you have it. And then I have, I guess, another picture of this, but I'll pause before I go to it if there's any comments or questions first. We're eager to see the next one. Okay, and so this is another example of this open source driver. The Bolsa is sort of the zoom in on that software stack that just focuses on Bolsa. This is something that I don't know if you folks have interest or don't have interest, but there is an ONF kickoff that will be, I think, next week, and they will be talking about driving this kind of software architecture forward and pulling in requirements from different partners. Okay. So, any other questions or comments? Software. No. Okay. All right. Well, thank you so much for that. And it's just about that time anyway. Why don't we shift gears and talk a little bit now about universal CPU.